Can PU cross PV be 0? FU, FV, they can be 0. Smoothness does not mean that it can't vanish actually, so it can vanish. But the third component is not 0, so this is never 0 actually. Okay? So this parameterization is a regular parameterization. Now I can see the surface. So this guy is going to be the surface. So I can see this set as the image set of all these points under the point P. And so in other words, that this surface S, जिसे मैं SF कह रहा हूँ, so I'm calling it SF, is really a legitimate surface actually. So you have to keep one thing in head. Now the word surface for us has a technical meaning. So I'm not using it a layman actually. We call, so in real life we call everything a surface actually. But now whenever we are calling mathematically surface, what we mean that it has a parameterization, okay, that is regular, okay, and has this property actually. That's what we mean. This guy, this example of this such kind of surface is also called a Mong patch. Mong patch. We're going to do differential geometry. This map P that we are now calling it parameterization, we're going to call it a patch afterward. So that would be a patch actually. We should call it a patch now. It's a Mong patch. Why this is a generic example? This is a generic example because what you can do, so think about now, say f of xy equal to say, f of xy equal to say x squared plus y squared. Okay, so only consider this f of xy equal to x squared plus y squared. So is it smooth? For sure smooth. And f of uv equal to, you define, okay, if we are using uv, then u squared plus v squared. Is it smooth?
Yes.
For sure smooth. There's nothing, it's a polynomial, so it must be smooth and continuous actually. Okay. Then, this collection of all such points, so uv and u square plus v square, okay, is a smooth map actually. It's a smooth map. It's a surface actually. Collection of all such points is going to be a surface. Okay, and you can go in GeoGebra and plot it actually. Okay, so whenever you are, for example, whenever you are taking a scalar field, okay, and you are plotting it in GeoGebra, any tool actually, so you are getting a surface. That surface is really, a graph surface actually, because what does that, GeoGebra is doing? So it's taking that f, this u square plus v square, okay, and it's making a graph of it actually. So it's a graph surface. Okay. So all kind of these surfaces are graph surface. So are you getting the point? So if you see this, so you can call this as a graph surface. Okay. So if you see a Pringle or a piece of chips, that is a surface actually, a graph surface actually. You can treat it as a graph, huh? Layers, something like that. Okay, it's a graph surface. Okay? So there are many things that can be treated as graph surfaces. Alright. So the other example, second example, so I'd like to talk about three examples, and these three examples are really fundamental in what do you call entire geometry. You're gonna learn, in differential geometry a result actually, or maybe in topology a result that would say that in 3 dimension you can have only two kind of the closed surfaces actually. So you can have two kind of surfaces. Okay. So either you're going to have a sphere or you're going to have a donut actually, or a torus. Or any other curve is just the combination of the spheres and donuts actually. The rest of things are just combination of spheres and donuts. So these are the pivotal and fundamental thing actually. Okay? So I can't get into topology now, but it's a very interesting, fascinating. So it's a classification theorem that, in a space you only have donuts and surfaces. The rest of things are just, for example, topologically, a line and a curve are the same thing. Think about it. So you take a line and just twist it. So the map is doing what? It's just taking a line and twisting it. These two things are the same thing actually. So in two dimension, you either have a line. So the line, curves, and all kind of curves, they are basically one kind of a manifold. Or you can have a circle. Then any closed figure, topologically, it's a circle actually. Okay? So imagine you have a circle made up of the rubber. So if you wish, you can turn it into a square. You can make an ellipse out of it. You can make all kind of closed figures out of it. Actually, so you're gonna say that all these figures, okay, which looks like different, basically are not topologically different. Anyway, it's a fascinating kind of analogy. Anyway, so the other two examples that I would like to talk about quickly is sphere and torus. Okay, so that's one example. So this will represent everything that is kind of, you have the open surface actually, which is not closed. So it's an open surface. Anything that is open. Okay. Intuitively. Open are not technically meaning open. Okay. In other words, that doesn't intersect with itself. Alright, so yeah. Here's the next thing, the sphere. Have you heard something about spherical coordinate?
Yes, we have.
Spherical coordinate. थोड़े हल्की आंच पे हैं. So imagine you want to reach. You are living on a spherical world. So as we are living on a spherical world, and you want to reach at some point actually. Okay. And imagine for now you are here, really in the middle of the sphere. Right in the middle of the core. Maybe your electron actually pop out of inside and outside. So you want to reach here. So what are you going to do? So what should I do?
Put a hole.
So the first thing would be that, okay, let's pop out of this, what do you call this angle? So how much distance I'm going to cover?
Radius of that.
R distance, and then
moving on the surface.
So another restriction is this, that you can't leave the surface, so you have to stay on the surface actually.
We will cover angles.
Okay. So you have to move this way, okay, by making some angle.
Yes.
Okay. So you reach here right in front of it, and then you will move this way. So what you call it, this angle? Longitude, latitude? What do you call it? क्या कहते हैं इसको?
Latitude के अंदर ये latitude होता है, ये longitude.
Okay. So you have to make an angle of, say for example, okay, u as a latitude, and then you have to move onto the surface and reach this point actually. So you can move this way actually and by making an angle. Actually. So you can reach to the any point of the surface. Okay? So pop out, make an angle, okay, and then we have this Euclid coordinates actually. So every point on the sphere can be described through these three fundamental quantities. Okay, these three fundamental quantities. Alright, so what is a sphere? So sphere is a map. Okay. What is the parameterization of this? I'm not getting into the more details of it, that's a topic of differential geometry, but let me just give you a parameterization basically of the sphere. So it's a map from, let's take a map from R2 to R3 for now, okay, and we will study the regularity of this map, and we'll see that, okay, what points we should include and exclude from R2 in order to make really a surface actually, to call sphere a surface, because to be a surface it has to satisfy the definition, okay, and define it in this manner. So the P of UV is, okay, here it's calling it A, so let's call this radius A actually. So it's going to be A cos U cos V, okay. We will get here, we can get into the details of it, that how did you get such an expression actually, okay. So that's not our concern for now. So this is your x component, A cos U cos V, and A sin U sin V, and A sin V. Okay, so A sin. What is the sex-theoretic representation of the sphere S2 with the radius A? So in rectangular coordinates, how do you write sphere? How do you define sphere actually, for example, in rectangular coordinates? So how do you define a circle in rectangular coordinates? So it's the collection of the points x, y such that x square plus y square is r square actually. Okay. So how does this is going to look like? Imagine that this ball is really the middle of x, y axis actually. So it's a collection of the points x, y, z such that x square plus y square plus z square is a square. Of course, I'm assuming that this sphere is sitting at
in origin.
at the middle, really at the origin of this x, y axis. Okay? This kind of a parameterization is called a geographical parameterization of the sphere. Now, is this sphere a surface? Can we call sphere a surface? So let's study that under what condition we can call this sphere a surface. So what basically you need to do. So is there any issue with the smoothness of the patch or the parameterization? So everything is smooth. Every component is smooth. Sine, cos, and they are smooth maps. You can differentiate them as much as band we like. So what would be the regularity?
Sir? So with what perspective they are named geographical parameterization, sir? The geographical parameterizations.
Okay. Alright. There are lots of ways to see. For people who are making maps actually. I mean, unless you understand maps correctly, maps are pretty, pretty tricky things actually. On a map, you can have a patch which looks smaller, but it's not really smaller actually. In originality, for example, you take a map, country है जो आपको छोटा लगे, ठीक है? और वो है साउथ या नॉर्थ पोल के करीब है, it's really near to the south and north pole. So it's gonna be really tricky because those countries or regions are not smaller in size as compared to the other, map, a country whose map looks bigger actually. Because it when you try to project something, so what is the key trouble? The key trouble is that imagine you have something two-dimensional, okay, or something sitting in a three dimension. The question is, can you project this spherical map onto the plane actually? The answer is no, without distortion. You can't do it. Okay, in other words, you can't take a plane and turn it into a sphere. No matter how hard you try and perfectly you do, there will be a hole always, at the poles of the basically spheres actually. So you can't make a perfect sphere out of something plain. And hence, you can't take a sphere and turn it into a plane. So what these experts of the map do, so they have created different kind of projections actually. That how you can take something, a map or something that is on sphere and project it on what do you call a plane actually. Okay. So this has a context. This has a context. We'll get more into when we're gonna do. So, but if you want to see, you can see stereographic projections actually. So just look for the stereographic projection. You're gonna find a lot of stuff. Okay. But that's a topic of differential geometry. ठीक है जी. So you have this parameterization of it. So is this a sphere? Is this a surface? So for this you need to compute what? PU cross PV. So I'm directly writing PU cross PV. So I'm not. I assume that you know how to compute the partial derivatives of the patches and how to compute the cross product of it. Okay. So I'm writing directly the cross product. The cross product of this is going to look like a square. Okay. Cos u cos square. Okay. V and sin u cos square v and cos v sin v. Okay, that's how it's going to look like. So you're going to compute it. Now, I mean, if you feel this looks very close to this actually. Okay, so if I take this one a inside and take, for example, the cos v from each of the component outside, then this is nothing. So a cos v times a PUV. Okay, you get the point? So take one a inside and take one cos v outside. So you're going to get a cos v and the same expression written. So you can call it PUV. Okay. Question: Can this PU cross PV be 0? The answer is yes. So what would be the magnitude of PU cross PV? So I want to find the points where the PU cross PV can be 0. So the PU cross PV can be 0. So what would be the magnitude of it? So that's a scalar. A cos V is a scalar. So this would be A cos V as it is times the magnitude of PUV. Magnitude of PUV. But what is the magnitude of PUV? So this is like your x, y and z, and you can really check that if you take x square plus y square. So this would be what? Okay, sin v cos v. So it's gonna be x square plus y square. Okay, so you should start from here actually. Okay, so.
सर
Are we
यहाँ
doing
पर
something?
कहाँ से
कहाँ पर?
बीच में साइन यू साइन वी लिखा
हाँ, sin u के साथ ये cos u है. Okay, so we have. ठीक है? A cos u cos p, a sin u cos v. Sorry, cos v. ठीक है? This must be cos v. Now think about it. So if you take, x square plus y square, so what are you gonna get?
Cos square u square. We will take cos square common.
So you're gonna get.
Cos square.
So it's gonna be a square
Cos
square v, right? And if you add a square cos square v into a square sin square v, so you're gonna get. So you're gonna get a square actually. So it satisfies this. It satisfies this concept. If you take this x and y and z, and you square three components and add them, so everything will turn out to be
a square.
a square. So what would be this guy? So the PUV square is a square.
It will be a, sir.
So it's gonna be a actually.
Yes, sir. By taking a square root.
So we have a square. Now, can cos v be 0?
Yes, sir.
Plenty of points actually. Plenty of points where cos v can be 0. And if the cos v is 0, then pu cross pv is 0. So if you want to find, a good domain for which you can say that P really defines a surface, you have to remove some points from R2. Okay? You have to remove some points from R2. Okay? And which should be those points? So these are those points. Huh? 2n plus 1 over 2 pi actually. So they can be, so in other words, your V So this guy is 0. So this magnitude of Pu cross Pv is 0 when V is this guy, what do you say, 2n plus 1 pi by 2. So all those, points where you have, so in other words, pi by 2 and 3 pi by 2 and all these points are the points where it is 0, where n is an integer. Okay?
Automatically from pi by 2.
Okay? You get the point? So if you want to define the domain of the function where this p will become sphere, it should be what? So remove all these points. Okay? And by removing all these points, how you can write it precisely, that let's define, for example, set un. Okay, so let me define a set un. So un is the collection of the points uv, okay, where u can be anything. There is no restriction on u. In other words, this pu cross pv and its magnitude doesn't depend on u actually. Okay, so no matter what you have, it's going to be basically this. So you take uv where the v is sitting between, so you have to put the restrictions on v. So you have to keep v stay away from such kind of points actually. Okay, and how you can write it, that v is say between 2n minus 1 pi by 2 to 2n plus 1 pi by 2. So that's un. What would be u naught, first of all? So the u naught is going to be minus pi by 2 to pi by 2. So if you take v between minus pi by 2 pi by 2, it's fine. This guy is not there. What would be u1? So it's going to be, between pi by 2 to 3 pi by 2. So these u's are basically, taking all care of all those points where the v is away from, the points where, this magnitude can vanish actually. Pu cross Pv can vanish. Okay. Let me write it precisely more. So what should be my u? What should be the domain of parameterization? So my domain of the parameterization is going to be the collection of all such sets actually. So the union of all such sets. Okay? So hence I'm going to say that P is going to be regular on a U, that U, which is the union of all these UNs where n is in Z. So that would be the domain for the P. So if you see P at its face value, it's not sphere. You have to remove some points from the domain actually, which are troublemaking. Okay? And the removing the points from the domain is going to be, okay, troublemaking, I know, but okay. But what? But what does it physically mean actually? So where is going to be V equal to pi by 2? So if this angle is V, so what will be the meaning of V equal to pi by 2? So it's going to be really, a point, for example, okay, so V equal to pi by 2 are the image of the points where the V is pi by 2 is going to lie on this line actually. In other words, you have to remove this point. This point are these entire points actually, the pole actually, what do you call it? The pole. So you have to remove this top point, not only top point, but the bottom point as well, because what would be the angle here?
Minus pi by 2.
Minus pi by 2. So you have to remove these poles. Okay, that's what physically it means. So this is topic in differential geometry. You're going to learn a lot there, but we're just talking about that. example.
यहाँ पे ये करना चाहें कि जितनी भी हमने पॉइंट्स ली हैं जो हम निकाल रहे हैं, निकालने की बजाय हम इसे रीपैरामीटराइज करें, तो वो भी कर सकते हैं.
That could be one of the thing, but I mean, if you remember, you proved that QU cross QV is, Jacobian of the phi times a PU cross PV. Now, if this is 0 at some point, this would be 0. ठीक है, reparameterize कैसे करेंगे? Through a diffeomorphism. So, जहाँ पर ये 0 हो रहा है, वहाँ पर ये भी 0 होगा. So, reparameterization will not solve the problem of regularity. Okay, maybe it would solve some problem of, could solve some other problems, but not the problems of regularity. Okay. So you parameterize things due to the number of reasons. You will see in differential geometry that we want to parameterize everything in the terms of its natural arc length parameterization actually. And there are very interesting results that are coming out of such kind of reparameterizations. Don't worry about it. So the sphere. Okay, so we are happy with this sphere. Now, if you take all these points, then P is a regular, so the P defines the surface. So you have to sacrifice some points out of the sphere actually, where you have to remove them because you are removing their corresponding inputs from the domain. So hence, outputs would not be there as well. Okay, so it will be a sphere, but there's going to be a sphere with a hole, pinched kind of sphere. Okay. For torus, okay, read torus for yourself. It has a parameterization, similar kind of a parameterization. Okay, and what? So when you compute PU cross PV for it, it turns out to be non-zero at all points actually. So you don't have that issue here. So it has that special kind of a parameterization. There are a number of ways in which you can understand torus actually. Okay, I can talk about it in several ways. Okay, torus will be a very important topic and an interesting topic in topology. Okay. So one glimpse I can give you is that. Okay, what is the meaning of R cross R? So it's just an aside. What is the meaning of R cross R? Physical meaning. How you compute R cross R?
Infinite planes.
So it's a plane, but how do you get that plane actually? How do you get that plane? So you say, imagine you have this line.
Perpendicular line. We will draw in.
You have this line. So I can see this as the union of, say, x cross R, where x is an R actually. Okay. I mean, it's okay if you understood it, it's okay if you don't understand it. But let's think about from this perspective. So what we say, so take a point from R and attach an R to it actually. So cross product कैसे लेते हैं? So you take a point from the first set and
multiply with all the
not multiply, but take this cross product related with all points in the R actually. Okay, relates with all points in R. Okay. So if I take one point in R, say for example this is origin. Okay. So what are all points that are related with the origin? You're gonna say that's this line actually.
vertical line.
So this line is the line actually that is attached to this point. Okay. And then we can see R cross R is that to each point in the real line you are attaching a line. So line, line, line. So there are lots and lots sorts of lines attached to every single point in R, and as a result you are getting a plane. Okay. What would be the meaning of R cross R2? Yeah, R cube for example. You can understand it in many manner. You can see it as R cross R2. What is the meaning of R cross
Assigning a
R2?
point, a plane.
Yeah, so to each point you are attaching a plane actually. And then you are combining all these planes. You get it? Three-dimensional space. But what will be the meaning of say R2 cross R?
Assigning a point from plane, a plane.
So take a plane and take each point of the plane and poke a line in it. It's not really vector field, but you can really imagine in your head